Hello, my name is Lapid and I'm Storage Field Application Engineer working for Micron Technology in Israel, supporting the high-tech industry, storage startups, and the storage ecosystem partners in the region. Today I'm going to talk about analyzing the effect of GPU storage on AI workloads. I'm very happy to be here with you on SDC EMEA and discuss about this topic. The agenda for today: I will address the question, can storage really impact AI training performance? I will present NVIDIA DALI as a proxy for benchmarking maximum throughput. And then we will go into NVIDIA GPU Direct Storage, the GDS, discuss briefly what it is, and then going to present Micron test results for local NVMe performance with GDS versus legacy datapath. The test was done in Micron Austin, which is essentially a data center that we used for performance benchmarks and testing new innovative hardware and software solutions together with our partners. Before I will dive into my topic, I would like to say a few words about Micron, for those of you who are not familiar with us. With headquarters in Boise, Idaho, US, we have more than 40,000 team members around the world in 17 countries. Israel is included. One important fact is that we are the fourth largest semiconductor company in the world, and we are very proud of our achievements over 40 years of establishment. So at first we wanted to check, can storage really impact the training performance? For that we use the server with 8 NVIDIA GPU V100 cards. The workloads were running as containers, which is typical to AI systems, and allow you to limit the resources in the system. We were working to limit the memory size and the disk speed of the system, and what we found is when we limited both, the training throughput is dramatically affected. And that's because we were using Resonant 50 model with ImageNet dataset, that with these GPUs really need 1 to 1.2 gigabyte per second training speed in order to load images from the SSD. What we see here is that when we had enough memory in the system, we affected only the first epoch in the system because that was reading from the SSD, and then the rest of it was done from the memory itself. And we had 1 terabyte of memory, which was enough to cover the dataset. So overall in your system, you will need either enough memory or fast storage, but it's really better to have both. Here is another benchmark that we did to demonstrate actually the same thing and lead us to the discussion about why are we talking about GDS. We were using NVIDIA data loading library, the DALI, for that. And this library is doing grid image, decoding that to a tensor that is used on an AI model, and then moving it to the GPU without any computational. What we found is that the results of TensorFlow training is very close to the maximum theoretical throughput that we get from DALI preload only. We got 18K images per second versus 23K images per second. And we figure out that with adding more storage to the system, we will not get beyond the maximal theoretical throughput because of architectural overheads that we had. That led us to talk about GPU Direct Storage and testing it in our lab. GDS, as we call it, moves data directly between GPUs and the storage devices without going to the CPU as a bounce buffer. This improve the throughput and reduce the latency, as we will see in next slides. So to test GDS, we use the following configuration. Supermicro server with 2 Intel Xeon CPUs, 28 cores each, 3 terabytes of DRAM, 8 NVIDIA V100 GPU cards, and of course 8 Micron NVMe datacenter SSDs. The SSDs were connected directly to the CPUs and not going through the PCIe switches. So first we wanted to check the CPU utilization by the worker count. And as we see here, for small worker counts, we had GDS had a slightly better throughput and slightly better core utilization. But as we scale the workers, we see dramatic improvement in both core utilization and the throughput. While legacy data path peaks at 12 workers, the GDS peaks at 64. So we wanted to check the CPU utilization by the IO size. And we chose 16 workers for that, because 16 workers were right after the peak of the legacy data path and way before the peak of GDS. And as we see here, there is a massive CPU savings for small IOs, small and even medium IOs. And the throughput is also improved in these data transfer sizes. So next thing we did, we wanted to check the latency of the system, because latency is, as you know, important in AI applications and really can affect the throughput of the training. And as we see here, we use the 16 workers as well, and GDS consistently reduced latency for small and medium transfer sizes. But when we go to the large transfer sizes, the architectural limitations is mitigated. So to summarize, the storage is clearly affect the training speed for AI applications, as we saw. GPU Direct Storage, with its reduced overheads of architecture, supplied considerable increases in the total throughput, and latency decreases significantly, together with the required lower CPU cores utilization. I've added here some additional collateral from Micron and from NVIDIA about this topic. Very interesting topic in my opinion. And you can also feel free to reach out directly to me for any questions or support. Thank you very much for listening, and goodbye.